Welcome to Beyond the Qubit. I'm your host, Frank Dekker. My guest of the day is Yuval Boger, the Chief Commercial Officer of QuEra. QuEra is an interesting party to talk to because QuEra makes a quantum computer based on natural atoms, and they have very exciting partnerships with MIT and Harvard. So thank you for being here, Yuval. I'm excited. Yeah. Maybe let's start with can you give us a short introduction of your journey in quantum technology? What sparked your first interest and how did you arrive at your role today?
Well, thank you. Thank you for the opportunity to be here, Frank. I have been in quantum for about 5 years now. Historically, I have always been attracted to frontier tech technologies, whether it's wireless power, virtual reality, or other things. By way of education, I have both a graduate degree in physics as well as a graduate degree of business. So it was always interesting for me to do things that have a scientific, a deep scientific background. I started my quantum journey at Classic, an Israeli software company that makes a software platform that allows you to quickly encode complex algorithms into multiple hardware platforms. And then after a couple of years, I transitioned to the dark side, to QuEra, which makes hardware. Almost is just as important as listening.
That's interesting. What I really like is that, and where you differentiated from my conversation so far, is most people cite things from the physics and from the technical. And you start with the customer and listening to the customer and customer curiosity. So I think that's an interesting observation. Maybe we can move to QuEra. Could you describe, in basic terms from somebody outside the quantum technology world, what is QuEra?
QuEra develops, manufactures, and installs and services quantum computers based on neutral atoms. Quantum computers, as we know, are expected to change the computational landscape, to be installed alongside the CPUs and GPUs in major data centers. Quantum computers are the subject of many well-funded national quantum programs because so many nations and organizations understand that quantum is a strategic technology because of the positive and also negative impact that it could bring. And there are many different ways to build quantum computers. Quantum computers, as you know, are based on qubits, quantum bits. And so how do you create these quantum bits? Well, there are companies that use superconducting qubits, like IBM. There are companies like Quantinuum that do trapped ions. There are other companies that use photons to create qubits. Well, we used individual neutral atoms. And neutral atoms, as I'm guessing we'll get into in a little bit, have tremendous advantages in the ability to ultimately create large-scale, error-corrected computers that are key to unleashing the potential of quantum. So QuEra, based in Boston, an outgrowth of amazing work that was done at Harvard and MIT, builds computers out of neutral atoms.
And can you explain me a little bit, what are the relationships with MIT and Harvard? And why is QuEra so close to both?
4 of the founders of QuEra were professors from Harvard and MIT. 2 from Harvard, Professor Lukin and Professor, sorry about that. So two founders were from Harvard and 2 founders were from MIT. And so that was the initial connection. But 2 of these founders continue to be, both Professor Lukin and Professor Vuletic, one from Harvard, one from MIT, continue to be super active in the company, both on the board of directors and in the day-to-day operations. But it's beyond these 2 amazing individuals. We think that even the physical proximity to Harvard and MIT, just a bike ride away, is really a strategic advantage of QuEra. Because what we've shown time and again is that we can take technology, I shouldn't say take, license or use or apply diffection that was developed at Harvard and MIT and very quickly turn it into a commercial product. There's a difference, there's a distance between an experiment that works in a lab, 10 minutes on a Thursday morning when the stars perfectly align, to something that can work repeatedly 100 plus hours a week. And so we were able to make that transition. Harvard and MIT is also a fantastic talent pipeline for us. We are sometimes very fortunate to be able to hire people who have graduated from Harvard and MIT. QuEra equipment is sometimes used at Harvard and MIT lab as we collaborate on experiments. And so there's really two-way contributions. And that's why, and that's one of the reasons that we are indeed the leader in neutral atom quantum computing.
It's an interesting story.
So we mentioned that
you want to have the computers to be better than classical computers, and currently there are not a lot of applications for a quantum computer where a quantum computer is better excels versus a classical computer.
Yeah, so quantum computers are a little bit useless right now in terms that there's not many problems that you can solve on a quantum computer that you cannot solve classically. There are some, but very few. And therefore, quantum computers are primarily used to prepare for the time where quantum computers will really be useful. And that's what we're trying to build. We're trying to build truly useful, powerful quantum computers that will allow solving these problems. Now, that means quantum computers that have enough qubits and good enough qubits. So larger and error-corrected quantum computers. Roughly speaking, let's assume we had perfect qubits, no errors. Maybe we'll talk about error correction a little bit later. But if you have fewer than 50 or 55 qubits, then you could simulate it perfectly on a supercomputer. So you don't need a quantum computer. If you only have 20 qubits, then why bother, right? Life gets interesting when you have hundreds or thousands or tens of thousands of really good qubits. Then you could solve amazing problems. So our vision in 5 years, but maybe not just in 5 years, I think it will be sooner, is to build computers that are large enough and powerful enough to solve some of the most pressing problems, whether in chemistry or material science or financial services or optimization, climate change, artificial intelligence, and so on.
That's really exciting to work on. Maybe, I think we will not escape it. Let's dive into the technology. Can you explain in basic terms how the technology of QuEra works? And then especially neutral atoms.
So as we discussed briefly before, each qubit is an atom, is an individual atom. And that's great. Atoms are, by design, they're perfect. They're perfect in terms of being perfectly identical. We could take 1 billion atoms and they will all look exactly the same. There are no manufacturing inconsistencies. We don't have to worry about this atom is greener or bigger or heavier than this other atom.
And Yuval, is it correct that it is not for all quantum technologies that all the qubits are exactly, or the atoms are exactly the same? Because some use a lot of calibration. Is it correct to say that some use a lot of calibration tools or control systems too?
Yeah, it is true, but I think the fundamental difference is that some qubits, like our qubits, are natural, and some qubits are manufactured. So when you make a superconducting qubit, you're basically creating a circuit, and that circuit may have inconsistencies, may have defects. Neutral atoms are perfect. And then we take these neutral atoms and we...
Can we go maybe a little bit more deeper in? So why are those atoms neutral and why are they so perfect? Could you elaborate a little bit on that?
Well, they're neutral because they're not charged, they don't have the number of protons and electrons is the same, and so they're not ions. That's a different way of creating quantum computers with trapped ions. And so they're neutral. They're not significantly impacted by electrical charge. They can be next to each other. We'll talk about how we do gates and so on. But we basically, in our case, we use rubidium atoms. Rubidium is on the left side of the periodic table, a few rows under hydrogen. And then we take these rubidium atoms and capture them in what's called laser tweezers. And so if you've seen bank robbery movies, I'm sure you have, right? You're in financial services, yeah. If you've seen bank robbery movies, there's always a scene, or there's often a scene, where the thief goes into the safe, and the safe has these laser beams from all directions that trigger the alarm system. And so think about sort of an array of laser beams coming from the ceiling, and magically, each of these lasers can trap a single atom. And by trapping means it creates an energy field that makes the atom want to stay really in the center of the beam. And that's super important. So first we trap these atoms in the laser beams. Then we use a combination of laser and electromagnetic fields to basically keep the atoms still, so they don't move. And there's a physical relationship between temperature and movement. So when we keep atoms still, it's really equivalent to us cooling them to almost absolute zero temperature. So this is, and through this discussion, you sort of understand some of the benefits of neutral atoms. So we start with perfect atoms, so there's no calibration issues. We cool them using lasers. I know when people think about lasers, oh, I'm going to heat something with a laser. No, but in our case, we cool something with a laser. And so we don't require cryogenic cooling. If you were to Google quantum computers, it's often that you'll find these beautiful chandeliers, golden chandeliers, which are associated with cryogenic coolings. They have various cooling stages. But cryogenic cooling is a nightmare. Is a nightmare for people who want to install quantum computers because they take up a lot of space, they take up a lot of energy, they require refills of the gas used to do the cooling. So we basically have a system that operates at room temperature that does not need this cryogenic factory. Then we spoke about the laser beams, where each laser beam captures an atom. Now, amazingly, if the laser beam moves, the atom moves with it. So all of a sudden, we have a situation where we can take any two atoms, any two qubits, and at will sort of bring them together or take them apart or take them to different places. In sort of semi-technical terms, we call this all-to-all connectivity, meaning we can bring any qubit to interact with any other qubit. And this is in contrast with approaches like superconducting qubits. Superconducting qubits basically have a printed circuit, and every qubit can only interact with nearby qubits, whether it's 2 or 4 or 5 nearby qubits. And why is that important?
One of my recent research questions at the moment, Yuval, is it possible to solve that problem, what you described, with input and output transistors? But I think if not, then for the error correction ratio, that's probably your next point.
So we can move the atoms around, and let's sort of take an example to understand why it's important. Let's assume that you and I go to a cocktail party, and I recognize you and I say, "Oh, I've had this amazing conversation with Frank a couple of weeks ago, and I want to go and talk to you again." If I'm a neutral atom qubit, I just walk over and say, "Hey, Frank, how are you doing? It's good to see you." And then we have a conversation. If I'm a superconducting qubit, I can't directly talk to you because you're on the other side of the room. So I have to ask the person standing next to me to relay a message to the person standing next to her, and then again and again. So it takes multiple hops until we can interact. And of course, with multiple hops, like the kids sometimes play a game of telephone, the message could be corrupted by the time it gets to you. And so the ability to move qubits around, to shuttle qubits around, allows us to create algorithms that are more efficient. They need fewer operations, allows us to create error correction codes that cannot be done in static configuration. So really a very, very big deal. The other nice thing about neutral atoms is these atoms are, of course, they're small. An atom is very small, but we can put them to be very tightly spaced. In our system, atoms are about 4 microns, 4 millionths of a meter apart. And that means that, in something on the size of my fingernail, we could put thousands of atoms. So at least from that perspective, it's very easy to scale. Now, when we speak about scaling, that brings us to another advantage of neutral atoms. How do you create operations on neutral atom? How do you make a neutral atom change its state or interact with another qubit? Well, that works through different laser beams. So, electrons in the atom have energy levels. They can be, usually they're, say, in the ground state. They can be in excited state. And we can sort of shoot a laser at an atom and make the electron move to a higher energy state. That transition allows us to make atoms interact. So, for instance, one key point in neutral atoms is what's called the Rydberg blockade. When an atom is in the ground state, the low energy state, you can think about it as being fairly small. When it's in a very high excited state, it feels like it's a huge atom, very, very big. Why does that matter? Because when atoms are in the ground state and they're fairly close to each other, they're fine. They're indifferent to each other. But when they're excited, they can't both occupy the same space. So actually, Rydberg blockade means that if atoms are sufficiently close, then you cannot have two atoms in an excited state nearby. And that, if you think about sort of classical analogies, that's like an exclusive OR, XOR operator on bits, where you can say only one bit can be one, but not the other, right? And so by shooting lasers at atoms, we can make them interact. Now, a laser beam we can shine a laser beam at multiple atoms at the same time. So we can have multiple atoms be operated on, multiple pairs of atoms. And so this parallelism also allows for more efficient algorithms for better error correction. And it also talks about...
Can you quantify a little bit, what are the limits there?
What are the limits?
What are the trade-offs? So if you increase the amount of neutral atoms created by one laser, but you can also have multiple lasers, what are the trade-offs there? On performance, on energy usage?
Of course, there are always trade-offs in engineering. We spoke about each atom is held by a laser beam with these optical tweezers. Well, if you wanted more atoms, you need either more lasers or more powerful lasers. More powerful lasers are maybe a little bit more difficult to stabilize in terms of their intensity or other parameters. So you get into sort of a lot of very interesting engineering challenges on how to scale the system. But just going back to that parallel operation of being able to use a single laser to operate on multiple qubits, I go back to the superconducting qubits. A superconducting qubit, each qubit would have 2 or 3 wires, 2 or 3 controls connected to it. That sounds fine. But let's assume you need 1 million qubits. Then you're going to have what, 2 million wires, 3 million wires? That's going to be, that's difficult. It's difficult to route. It's difficult to control. It takes a lot of weight and size and space, right? How do you make sure that there's no crosstalk between electrical signals on the wires? And in contrast, neutral atoms scale by just having, I'm making it a little bit simpler than it is, but just having a bigger laser. When you scale a superconducting system, the number of controls scales linearly with the number of qubits. When you make a neutral atom system, the number of controls scales maybe logarithmically with the number of qubits. So it's much, much easier to get to larger number of qubits. And indeed, so for instance, a couple of weeks ago, a team at Caltech demonstrated 6,000 qubits on a single machine, 6,000 neutral atom qubits on a single machine. Harvard published a paper with 3,000 or so qubits on a single machine. These are numbers that you don't see yet in superconducting qubits. Superconducting qubits also create a chip. Now, if you wanted to put 10,000, 100,000 wires on qubits on a chip, well, one, it would be a large chip. But the other thing is you get into sort of impossible yield situations. How many qubits are going to be bad, and what do you do about them? And so what manufacturers typically do is they say, well, we're only going to limit the chip to a few hundred qubits, because that we can get sort of a decent balance between manufacturability, size, and yield, and so on. But how do you get to 1,000,000 qubits if your chip has, say 500 qubits? Well, you're going to need 2,000 of these chips. You need to network them. That creates additional complexities and issues with errors, with software complexity, with optical links, and so on and so on. So life is so much easier if you could just put a lot of qubits, thousands or maybe tens of thousands or hundreds of thousands of qubits on a single machine. So for all these reasons, room temperature operation, perfect qubits, parallel operations, flexible connectivity, and scaling, this is why, as you can tell, this is why I'm so excited about neutral atoms. Make a correction and then continue on and on. And the hope, and we at QuEra are one of the leaders in quantum error correction, but the hope is by doing that correctly, you'll be able to really fulfill the promise of quantum, which is creating and solving these really complex problems that couldn't be done.
Yuval, can you maybe, you said, QuEra is leader in this field. When I interviewed Jan Goets from IQM, he said, on superconducting, at the moment we are between 700 and 1,000 physical qubits, error correction ratio to one logical qubit, but he expected it to be around 2033, around 20 or 30 physical qubits for one logical qubits. And they were moving to, even though they were on superconducting, he expected them to move to new error correction methods. But so let's assume that he's wrong and they don't move to 2030, but they move to 50. But where is QuEra today on the error correction ratio, and what is the progress you see on the 5 or 10 year view?
So let's talk about logical qubits and error correction. First, let's go back to giving a classical example just to illustrate this. Let's assume that you and I were talking, and I'm outside. I'm not sitting in the room. I'm sitting outside, and there's wind, and so sometimes you don't hear me very well. And I want to give you my credit card number. And it's really important that you get it correctly because you're going to make this really important purchase. And if you get one of the digits wrong, then that's not going to work, right? So one way to go about it is, if you can't hear me really well, maybe I repeat every digit several times. So maybe if my card begins with 4 and 5, I say, hey, Frank, it's 444, 555, and then I continue to the other digits. So by repeating every digit 3 times, I increase the chance that you'll be able to hear enough times correctly. Now, if it was really windy, or it was even more important that you get the numbers correctly, maybe I repeat each digit 5 times, or maybe I repeat each digit 23 times, right? So the more times I repeat it in this simple case, the lower error rate you're going to get. Maybe you move from 1 in 1,000 to 1 in 1,000,000. So first, when you think about logical qubits, they're not all created the same. What is the error in the underlying physical qubits? Obviously, the better physical qubits, the easier it's going to be to make good logical qubits. Then you ask yourself, how many errors could I overcome? Could I overcome just 1 error? Could I overcome 2 errors? Can I fix them? Can I not fix them? And so there are many, many different ways.
This also has to do with the steps and the depth of the calculations. Is that correct?
Right. Yeah. So there are many, many different ways to build logical qubits. Having said that, you can imagine that if I can move qubits around and if I can make parallel operations, then I have methods that are not available to me if my qubits are static. Let me give you a sort of a simple example, using my hands. Let's assume that my hand is a logical qubit, and it's got 5 physical qubits, right? So they kind of move together, and that's how we use to correct. And let's assume that this other hand, so I've got 2 hands, and they're both logical qubits, right? 5 here and 5 there. Now, if I wanted to make an operation between them, I basically want to make an operation between every qubit in each group. So I want to make between, this finger and so on and so on, every pair of fingers. If I'm a neutral atom qubits, I can take one hand, basically bring it to be almost overlapping with the other hand, and now with a single pulse of light, create that operation, execute that operation between every physical qubit, all at the same time. If I'm a static qubit, I can't do that all simultaneously. I have to do that one by one. When I do that one by one, errors can propagate, because if there was an error in the second pair, maybe it propagates to the third pair. So by doing parallel operations, I can reduce the number of errors, and by moving them around and having flexibility in the connectivity, we can make more efficient codes. So I'm really glad that
I have an analogy that pops up in my head. I don't know if it's correct, but let's check. I'm quite close to the telecom operators. And you have fixed line operators and you have wireless operators. The benefit of the fixed line operators is they are connected with fiber. So they have very good throughput. Mm-hmm. And the reliability is very hard. But it's quite costly to connect one endpoint to another endpoint because you have to draw a fiber between them. That's maybe the superconducting approach or other. And you're saying, no, look, our atoms are mobile, wireless, and you don't need the cables, and we can bring them very closely, and we make a wireless connection without the cables. Is it a correct?
Yeah, that's analogy? A reasonable analogy. But now let's see what it means. So let's assume that I was a fixed operator, right?
Yes.
And so I have 3 points, three exchanges. So I've got one exchange A connected to B and exchange B connected to C. What happens if exchange B goes down? Oh my God, now A and C are no longer connected, right? Because they used to go through B and now nothing happens. But if my tower is on a truck and I can just drive the truck over, then I'm able to overcome the fact that B is now gone because now I can create a direct connection between A and C. It gives me that ability to move my towers, my atoms, my qubits around, allows me to have greater flexibility in that.
And what I wonder is, typically the fixed line connectivity, the fiber, is better than the wireless connectivity. Because with wireless, if you have a wireless, let's say you have a 5G or a Wi-Fi signal, then if there's a magnetron in the room or if there's other noise, it's more susceptible to noise. But the fiber is more in a controlled environment. What is the trade-off there between the two? So I think it's a massive benefit. The wireless is a massive benefit. But what is the trade-off? And how can you mitigate the risk of that the wireless connectivity has more risk for?
Well, like many analogies, this analogy also has its limits.
Yes.
Right. And so you can think about, if you go 5 years back in time, we were all, young and handsome, right? People used to say, yeah, we understand that neutral atoms are exciting and they got all this potential, but the operations are not high fidelity. We've got a lot of errors, It's not that you're succeeding 99% of the time, you're succeeding only 95% of the time, and that's not good enough. That was some years ago. But neutral atoms have made this dramatic improvement where the fidelities are at least as good as superconducting qubits. And therefore, some people say that neutral atoms move from being the dark horse of quantum computing to being the workhorse of quantum computing. Because now you can do all these amazing things with them.
And what caused that? What caused the fidelities to significantly improve?
Well, people like Professor Vuletic and Professor Lukin and scientists at QuEra and scientists in other institutions that are not affiliated with QuEra have done amazing work on finding, improving the science, improving the technology, improving the calibration, figuring out where noise is coming from, and doing that. Maybe better lasers, better controls, finer this, so many different things have happened.
And going forward, because, for example, with self-driving cars, they say it's not about reaching the 99, but it is about the 5 nines, 99.99999. It's really about what's behind the 99 point.
Well,
and then do you need to would you use photonics to do that, or can you keep them in neutral atoms, or how can you do the connection? How would that work?
So I think for every modality, scale out is a possibility. For some modalities, it's more urgent because they can only do small chips or a small number of qubits in the machine. I think most people think about optical networking as sort of the way to optical links is the way to entangle adjacent machines, and of course that means that you have to potentially make a conversion between whatever modality that you're using, superconducting or something else, to photonics. How fast is that link? What are the errors? How does that impact connectivity? If I have a 10,000 qubits where every qubit is connected to every other qubit, but now I have a link between groups of 10,000 qubits, that introduces software issues as well. I think that's one of the perceived advantages of photonic quantum computers, that they say, well, everything is photons anyway, so we're not worried that much about connecting. I mean, we are connecting all the time. So yes, we are thinking about how to interconnect machines and what that means. The good news is that for us, it's less urgent than some of the other modalities.
Mm-hmm. But I think to your point on the medical exam, if you have to study and prepare for it, I think that really scales. So now with AI, and AI is absolutely different than quantum computing because you have no entanglement and no superpositioning. But now they're going from 10,000 GPU clusters in 2023 to 100,000 in 2024 to 1 million in 2027 and potentially 3 million in 2030. So that was massive. That if you're able to do scale up, that would bring massive benefits.
Yep, brings lots of benefits, and it brings lots of complexity. So I agree with you. It will need to happen. We are working through some of what we think is the best way to do so. And ultimately, yes, computers will be networked, whether just to scale out, or sometimes you can almost think it's not exactly like the internet, but you could say, can I distribute a calculation between computers that are far away? If you have a big quantum computer and I have a big quantum computer, can we somehow network them together to solve an even bigger problem? But that's sometime into the future.
Yes, and maybe to summarize to your point, this is not where the focus is on right now for neutral atoms, because you have a natural way of scaling the amount of qubits per system.
Right, that's not the most urgent thing, yeah.
Yes, and that is where the focus and the priority is at the moment, so you're not reliant on. And then the third element, the error correction ratio, and that's where you were also quite bullish on. Could you walk us through the improvement? So where are you today on physical to logical qubits, the error correction ratio, and how do you expect that to develop for the coming 5 and 10 years?
The code itself, I mean, so we have lots of flexibility in the codes, and actually in our systems we're demonstrating different codes, which is also some of the power of the flexible connectivity between the atoms. What ultimately matters is the number of logical qubits and the logical error rate, meaning is it 1 in a million? Is it 10 to the minus 8? Is it 10 to the minus 10? And so on. And so we're getting better and better. You know, we're moving towards hundreds and in the future thousands of logical qubits. We're moving towards error rates that are truly meaningful. I'm not going to reveal our entire roadmap on this podcast right now. That's probably coming in a couple of weeks. But yeah, that's obviously an area that we engage with customers in 3 ways. One is we allow them to use our computers over the cloud. Our first computer, it's a 256 qubit machine, is available on the cloud through Amazon since November of 22. So we're very close to celebrating its 3rd birthday. And it's been used by hundreds of organizations around the world, JP Morgan, BMW, many others. It's been used to create some groundbreaking scientific research. And so we definitely see use. And when we started with QuEra, that computer, we only had it available for 10 hours a week. Now we have available for 130 hours a week, almost the entire week. Part of that was we got better at running it, but part of that was demand. I mean, we just didn't want to have customers wait 2 weeks to get time on the computer. So we've got real proof that customers do very interesting stuff with it. The second way we engage with customers is by selling them a machine for on-premise delivery because they want it in their data center or in their country. And so, for instance, last year we announced a really important deal with AIST, the Japanese Institute of Standard and Technology. We sold them a computer. We installed it recently for over $40 million. So that's proof. Someone is willing to pay you $40 million, then surely they think you have something that's truly valuable and interesting. And the third way we engage with customers is by doing co-design. That work of optimizing hardware to software and vice versa. And so, for instance, we recently published work that we did with Los Alamos National Labs in the US. We published work that we did with American Amgen and Deloitte. So we're doing algorithm development projects with customers. So cloud, on-premise, or co-design. We are seeing momentum and we're seeing success in each and every one of these fields.
That's clear. Thank you. How do you see the total addressable market for neutral atoms?
The total addressable market for quantum computing is tiny today relative to what it's going to be in 5 years because quantum computers are not as useful as they will be.
Let's say 10 years, I think, because
we're not worried about total addressable market because quantum computing can impact essentially every single market vertical. When you think about key applications for quantum computing, people think about simulation, they think about optimization and machine learning. And give me an industry and I'll tell you simulation problems that they have, optimization problems that they have, and machine learning. So these are horizontal applications that can impact and transform practically any industry. And so we're leaving the estimations to companies like BCG that are, by the way, one of the QuEra Quantum Alliance partners that estimate billions and billions of dollars in addressable market. Probably they're pessimistic. I mean, I think it's going to be much more. We're not worried about the market. We're worried about how quickly can we build large enough error-corrected computers that people can use.
Okay, that's clear. And when would your conviction go up, Yuval, that neutral atoms are scaling? What do you need to see? Which 2 or 3 data points and say, well, Frank, if that happens the coming 3 or 5 years, then my conviction goes up that we made it.
What I've seen, I've been 3 years at QuEra, give or take, a little bit over 3 years. And in these 3 years, because of the hard work that our scientists and engineers have done, challenges have transitioned from being primarily scientific challenges, we don't know if we can do that, to primarily engineering challenges. Yeah, we can do that, but now let's make it reliable and scalable and manufacturable and so on. So in that sense, although it's not truly a straight line, my conviction goes up every day because we're knocking out the scientific problems. They still remain, every time we get to a peak of a mountain, we say, okay, what's the next mountain that we can reach, right? Yeah, 3 years ago, putting a system with 256 qubits online was just an amazing achievement. And 3 years later, Harvard is publishing, 3,000 qubits that operate continuously. And it's just, the rate of progress is stunning. And that's one of the reasons that I so much enjoy being in this market.
I can imagine. Okay, then can you walk us through the positive flywheel? So why can QuEra innovate the fastest and why are you the best longer term?
Well, let me start from the second part of your question. We believe that neutral atoms is the best modality. And that's because of room temperature operation, perfect qubits, all-to-all connectivity, scalability, all the things that we discussed previously in the podcast. And so we believe that neutral atoms is the best way to get to quantum computer. And we believe that quantum is both the scientific and commercial leader in neutral atoms because we have shown that we can deliver systems, that we can put systems online, that we can run error correction like no one else. So we are convinced that we are today the leader in neutral atoms, which happens to be the best modality. That doesn't mean we have to continue running, right? We have to continue innovating and hiring great people, making sure we have enough money, and so on. So that's all there. But the flywheel comes from creating better systems and at the same time listening to what customers want. Listening to what customers want, working with customers. Oh, we tried to do this. It didn't work. Why did it not work? Okay, we did this with 200 qubits. Is that good enough for you? Okay, what? No, it's not good enough. Why is it not good enough? What do you really need? And that listening to customers and then being able to quickly transition it into adjusting our work plan accordingly, that the proximity to Harvard and MIT and the quality of people that we have and the quality and amount of backers that we have make us very optimistic about the success of QuEra.
I've got two more questions. One is, how much capital do you need?
Well, building quantum computers is expensive. We're fortunate to have done a very nice raise, $230 million led by Google and SoftBank. And of course, with our existing investors, NVIDIA also joined. We need enough money to operate. There's a risk to having too much money. If you have too much money, then maybe you're not taking care of it the right way, so to speak. Maybe you're having the right amount of money, and I think we are at that sweet spot. Remember that commercial companies also need to be able to return money to investors and return a profit. So if you raise $2 billion and your investors, you raise $2 billion and and let's say you gave up 20% of the company for that, then that means the company has to sell or IPO for much, much more for the investors to make a good profit. So we're not here just for the science, we're also here for the business. One thing that, although is implicit in what we spoke about neutral atoms, is when you go to vendors, you should ask them, okay, let's assume you need 1 million qubits to make something truly useful. How large is it going to be physically? How much is it going to cost? And how much energy does it consume? And some of the approaches that we're seeing are saying, oh yeah, we need a football field. It's going to cost $1 billion and it's going to require 100 megawatts of power. That reminds me of a B-2 bomber. A B-2 bomber, a very unique plane that costs $2 billion and of which 20 or 20 something were made. We think that because we don't need cryogenic cooling, we operate at room temperature, because we can put lots of qubits on a single machine, then our machines will be much smaller physically, they will be much more affordable, and therefore a much larger group of people can afford them, and they will require tens of kilowatts of powers and not tens of megawatts. So if I were just to continue the airline analogy, I think we're building the 777, the Boeing 777, or if you want the Airbus A3, right, or of quantum, not the B2. We think that this is the right technology to make something that's truly useful and widely available to anyone, any friendly organization that can use it.